Hi, my name is Bill Kinney, and this is my 13th video helping budding actuaries to prepare for their exam on probability. But you might be saying, wait a minute, I don't want to be an actuary, or maybe I don't even know what an actuary is. That's okay. You can still get benefit out of this video to learn about conditional probability, disease testing, and Bayes' theorem. Okay? It'll still be beneficial content for you. Like I said, it is video number 13. It's a question number 725 from the SOA Sample Exam P questions. SOA stands for Society of Actuaries. Exam P stands for an exam on probability. You need to know some background, so if you are rusty on probability or if you don't know much, you should watch the first 12 videos before this point to really get warmed up for this kind of video. We're going to be solving for a conditional probability with something called the special addition rule for mutually exclusive events, and the general multiplication rule. I've talked about these rules in previous videos. In this video, I'm going to also introduce tree diagrams and something called Bayes' theorem. I think I'll do Bayes' theorem first and do tree diagrams at the end. However, in future videos, it turns out that the tree diagrams are usually the quickest way to solve a problem involving Bayes' theorem. So question number 25 says, a blood test indicates the presence of a particular disease 95% of the time when the disease is actually known to be present for some other reason. That's called a correct positive result. Positive meaning you have the disease, although that is a bad thing, but the test is coming back positive, saying you have the disease. The same test indicates the presence of the disease in 1/2% of the time when the disease is not actually present. That's called a false positive. It's saying you have the disease when you really don't. Okay, that's happening infrequently, 1 out of every 200 times, but it does happen sometimes. 1% of the population, everybody, actually has the disease. Okay, so that's another bit of given information. You go into the doctor, you take this blood test. Maybe it comes back positive. You're wondering, oh boy, it came back positive. What are my chances that I have the disease? Calculate the probability that a person actually has the disease, given that. The phrase given that means we're going to compute a conditional probability. The test indicates the presence of the disease. It comes back positive. It says, yes, you have the disease, but you might not. Okay, that's what we want to figure out. If you didn't know much about probability, you might be tempted to say the answer must be 95% here, but it's actually not. It's something different. Okay, so to start with, I've been usually making Venn diagrams to help us solve problems, and I will do that in this video. But let's just first start by writing down the given information. What are we given? We're going to use standard probability notation. You've got the 95% here and the 0.5%. Those could be thought of as representing probabilities. What kind of probabilities? P stands for probability. Well, the 95% is saying if this person is known to have the disease, it's going to come back positive. Yes, they have the disease in 95% of those situations. The probability of the test coming back positive, yes, you have the disease when it is given that. This vertical line means given that, or known that. Given that is what that says. If it is given that they have the disease, let's call the disease D, that's 0.95. So that's one piece of given information in the problem itself. That's a conditional probability. This 0.5%, 1/2%, is also a conditional probability. If you know they do not have the disease, D prime, the complement of D, is what is given. What is the probability that it comes back positive? Yes, they have a disease in spite of the fact that they are known to not have the disease, assuming you know for sure they don't have the disease. 0.5% as a decimal is 0.005. So that's another piece of given information. We also know that 1% of the entire population, everybody, has the disease. The unconditional probability of having the disease is 0.01. So these are our givens. What do we want to find? We want to find another conditional probability. Remember I said pretend you're going into the doctor, getting this test done, and the test comes back, yes, you have the disease. It comes back positive. What are the chances that you really have the disease? That's a conditional probability where the y and the d are switched around. What is the conditional probability of having the disease given that the test comes back positive? It's not the same as this conditional probability. Okay? So before we think about this in terms of formulas, let's go ahead and draw a Venn diagram in a way that I think will be helpful for conceptualizing a reasonable ballpark for the answer and why the answer is not necessarily 0.95 and in fact is likely to be different. So you draw a box here, and I'm going to pretend this box that everybody in the whole world is standing inside that box. Okay, pretend that. And I'm going to break the box up into pieces, first of all, based on whether they have the disease or not. Now, only 1% of the population, 1 out of every 100 people, have a disease. I'm going to use a rectangle here, a skinny rectangle that I'll shade red to represent those people that have the disease. So the people that are standing inside that skinny rectangle, pretending this is some huge floor here, are the people that have the disease. You can pretend that the area of this thing is 1% of the whole area. Okay, I drew it bigger than 1%, but you could pretend. All right, so that's D, which means the complement of D is everything over here. These are the people that do not have the disease. That's D prime over there, this big white area. Okay. Then we're also thinking about people getting this test done, pretending everybody in the whole world, in fact, gets the test done. Okay, just for the sake of pretending. And some of them get a positive test result and some of them don't. The fact that this conditional probability is 95% means that if you shrink your sample space to just considering these people that are standing inside this red rectangle who are known to have the disease, 95% of them will get a positive test result. So that the relative area of this green box that I'm shading inside the red box, it's going to be 95% of the area of the red box. Okay, that's what this 0.95 would mean if I'm trying to visualize probabilities as areas. What about this conditional probability? There, the given that is D prime when they are known to not have the disease. Those are the people that are standing over here. 1/2 of 1% of them have a test that comes back positive, falsely. Gives a yes result, even though they don't have the disease. So if I focus on that box and draw another sub-rectangle of that I'm imagining to be real small. In fact, I'm imagining this to be 1/2 of 1% of the entire area of the white box. That would then represent this conditional probability, the fact that this is 1/2 of 1%, 0.5% of the entire area of the white box. Now think about what we want to find. We want to find the conditional probability of having the disease if it is given that or known that the test comes back positive. Yes, you have the disease. That would be a situation where you're in one of these green rectangles. The green rectangles here mean the test comes back positive. So you've shrunk the sample space to being in this L-shaped region here. The question now is, what is the probability that you have the disease? Thinking in terms of areas, it would be the size of this area, of this rectangle, the area of this rectangle, compared to the entire area of the two rectangles combined. Of course, the picture is not accurate, but it's reasonable to see here that the answer may not be very close to 0.95. It could be a lot smaller, okay? Perhaps in the ballpark of somewhere between 0.3 and 0.7 or something, okay? But we actually have to go through the calculations to see if that's true or not. Okay, so what should we do? As far as using the rules, I did talk about wanting to use the special addition rule for mutually exclusive events and the general multiplication rule to help me solve this. The general multiplication rule is what I'm going to use right away in the form of what's really the definition of conditional probability. So here again is the conditional probability that I want to find. The probability of having the disease if it is given that the test comes back positive. By definition, that's really the probability of a randomly chosen person having both the disease and the test coming back positive. I'm using the intersection symbol there to mean and. That's the intersection symbol. It basically means and. Okay? And I divide by the probability of y, the probability for a randomly chosen person that the test comes back positive. These are unconditional probabilities. This is really the definition of conditional probability. It could be thought of as the general multiplication rule as well if I multiply both sides by p of y. assuming P of y is non-zero here, by the way. So that's the first thing to use. The next thing to use is the general multiplication rule again, as well as one other thing that I'm going to do. I'm going to use the general multiplication rule on top here to find the probability of dny occurring, but not using this conditional probability, but instead using this conditional probability. The probability of dny could be thought of as this conditional probability up here, the probability of y given d, times the unconditional probability of d. That's the general multiplication rule, if I think of it in terms of this conditional probability. So again, if this is something that's new to you, if you've never heard of the general multiplication rule, it's simply something you're going to want to look up or watch some videos before you come to this point. So notice again that I'm using this conditional probability here, which I know, 0.95, instead of the conditional probability that I'm trying to find. Okay, so that's important. Another thing that I'm going to do is I'm going to write y itself, which again over here is the L shape in green, as the union of two disjoint or mutually exclusive events. This green rectangle here and this green rectangle here. I'm going to write y as that union. How could you represent this one over here? That's really y intersected with d. It's not including this part up here, by the way. That's y intersected with d, and I'm unioning that, combining it with this rectangle over here, which is really y intersect d prime. D prime is the entire white box originally, which also has this shaded part down here. That's y intersect d prime. Those are disjoint sets. They are non-overlapping. You can see in this picture, this rectangle in green and this rectangle in green have no overlap. The line that they share in common is not really an overlap. And therefore they're disjoint or mutually exclusive, and therefore the probability of their union, one or the other, union really stands for or, make that remark, union stands for or, is the sum of their probabilities. That's called the special addition rule for mutually exclusive events. Let's write that down here. So it's the probability of y intersect d plus the probability of y intersect d prime. On top I still have the conditional probability of y given d times the unconditional probability of d. Okay, we're getting close here. Hang on. Now I want to figure out what these probabilities are here and here using the general multiplication rule again. This is a pretty complicated kind of problem. Lots of different kinds of rules coming into play here. Bayes' theorem is not an easy thing to understand. This probability right here, I've already figured out. It's the same as this one. The roles of d and y can be switched around. D intersect y is the same as y intersect d. I can write it as this product, the same product that I have in the numerator of the fraction. Let's write that down here. P of y given d times p of d, just like I have in the top. P of y given d times p of d. And I can do a similar kind of thing right here, except replace the d with a d prime. This would be p of y given d prime times p of d prime. And all these numbers that you see in here are numbers that I am given. I know these numbers. Look up here. Okay? P of y given d, that's the 0.95. P of d, that's the 0.01. In the bottom denominator of the fraction, it's the same product here, 0.95 times 0.01, plus this product is going to be 0.005 times, okay, we don't see p of d prime up here, but I guess I'm using the complement rule as well. P of d prime is going to be 1 minus p of d. 1 minus 0.01 is 0.99. That needs to go there. Okay, so I need the complement rule as well. Now just do these calculations. 0.95 times 0.01 is going to be 0.0095. And then I also have, in the bottom right there, 0.005 times 0.99, 0.00495, add 0.0095, and then take 0.0095 divided by that. I'm going to, on this old calculator here, I'm going to take its reciprocal here and multiply times 0.0095. The answer is about 0.657. That is the correct answer. I've checked this ahead of time. It is choice B on the SOA sample exam problems. So you got about a 65.7% chance when this test comes back positive, saying yes, you have the disease, that you actually have the disease. It's not a 95% chance, it's less. And sometimes in these situations it can be even a lot smaller, okay? This answer could be small, especially if the disease is real rare. All right, that's how you solve the problem, thinking through things in terms of, again, these rules. Let's now write down Bayes' theorem. I'm not going to write it as a sentence structure. I'm just going to draw a picture and write a formula. And then I will also draw something called a tree diagram. That is a way you can structure your problem solving to solve these kinds of problems more quickly. You can see this problem took a while. So what does Bayes' theorem say, first of all? Again, I'm just going to draw a picture here. Bayes' theorem, if you're thinking of it in terms of a Venn diagram, starts by assuming, first of all, that you've got a bunch of disjoint, mutually exclusive events whose union is the entire sample space. Something like this is the way you could picture it. Call it B1, B2, B3, etc., up through, say, Bn. Just like up here, D and D prime are disjoint, mutually exclusive events, non-overlapping, whose union is the entire sample space. The union of these two rectangles, the skinny one here, including this part up there, and this whole thing here, including this part down there. Those are playing the role of B1 through Bn, D and D prime are, okay? And then you've got some other event that you're thinking about, call it A, and draw it in the middle here, say. Okay, A is going to represent Y in this problem. And you're given some information. You're given the probability of all the B's, just like we knew the probability of D, and we could figure out the probability of D prime easily. So let's see, we're given the probability of the BI's for all I, 1 equals 1 through n. And we're also given some conditional probabilities. We're given the conditional probability of A given BI. That's also for all I goes from 1 to n. Okay, so again, up here, thinking about the comparison here, D and D prime are going to play the role of a B1 and a B2, and Y is going to play the role of A. We knew the conditional probability of Y given D and the conditional probability of Y given D prime. We want to find for some J, say, the conditional probability of Bj given A. Okay, that's what Bayes' theorem will help you find. And the way you can write the formula is to say this equals the conditional probability of A given Bj, for this specific J here, we're talking about some specific J between 1 and n, times the unconditional probability of Bj, divided by the sum, notice the sum up here, of probabilities like this, except replace the J with, say, an I, and I is going to be the index of summation here. I is going to go from 1 to n. In the problem that we have up here, n is 2. Okay, we have, again, a B1 and a B2 representing D and D prime. Okay, so that's the formula in Bayes' theorem. Finally, let's draw a tree diagram. That again is going to be the quickest method for solving problems like this. So you don't have to rethink about all this. You can more quickly solve it. So what you want to do with the tree diagram is you draw branches. That's why it's called a tree diagram. And the starting set of branches represents the B's in this picture here. In our problem, it represents D and D prime, that you have the disease or you don't. Label the branches that you see here with the probabilities of each of those things. These are unconditional probabilities. We know the probability of having the disease is 0.01, and the probability, therefore, of not having the disease is 0.99. Those have to add up to 1. Then after you end those branches, continue 2 more branches in this case on whether the test comes back positive, yes, or negative, no, which is the same as y prime, the complement of y, and label these branches with conditional probabilities. We're given these conditional probabilities. For example, probability of y given d is 0.95, that would go here. And the probability of y given d prime is 0.005, that would go here. By the way, we can fill in these other branches in this diagram, even though it seems like we can't initially, because the numbers in these two branches have to add to 1. So this is 0.05. I hope that makes sense. For people who have the disease, the test either comes back positive or not. And these two branches have numbers that add to 1, so this has to be a 0.995. So besides being quicker in solving the problem, this can also help you solve other related problems. Then you, along each path through the tree, you multiply the numbers along the branches. 0.01 times 0.95 is 0.0095, put that there. 0.01 times 0.05 is 0.0005, put that there. 0.99 times 0.005, I checked on my calculator ahead of time, is 0.00495. And finally, 0.99 times 0.995, I guess I did this one there. 0.99 times 0.995 is something I checked on my calculator to be 0.98505. Then for our problem, we were focused on those people for whom the test came back positive. That would include the two y's, this one and this one. And the final ratio that we computed was this number divided by the sum of these two numbers to get the answer. So you could see how that would more quickly help you solve the problem. And again, like I mentioned just a minute ago, it can help you solve other problems. Like if I wanted to find the probability of having the disease if the test comes back negative, not positive. The tree diagram can help me quickly find that. I focus on the y primes instead of the y's, and I'd quickly see that I get 0.0005 divided by the sum of 0.0005 and 0.98505, and that ends up being about 0.0005073. Okay, a little bit bigger than 0.0005, but yes, a small chance of having the disease if the test comes back negative, so that's a good thing. Thanks for watching.